what we'll talk about in chapter 16 are all examples of nucleophilic acyl substitution. And you've seen this before in chapter 13 with both reduction and reactions and organolithium reactions. But we're going to talk about it more broadly. But just remember that if this is the carbonyl carbon, this is the oxygen, here is the Y group, and then we need another color, I guess, purple for the nucleophile. We end up with a tetrahedral intermediate where the leaving group and the nucleophile are both attached to the carbonyl carbon, and you've got a negatively charged oxygen, which can kick down and kick off the leaving group, as you've seen before. And then how efficient this process is really depends on how good the leaving group is, and also how nucleophilic or reactive the nucleophile is. We've dealt with issues before of, can the nucleophile attack first, or does the carbonyl need to be protonated first? And then what happens once you get here? Does the leaving group leave, or are you stuck with an addition reaction? For everything we'll talk about in chapter 16, we're going to be doing substitution reactions, which means leaving groups are going to leave, and nucleophiles are going to be left behind. What we're not going to do in chapter 16, or rather what we're not going to spend time on in class, are all the iterations of this that are easy, okay? So for example, let me give you an easy iteration of what I've just shown you, and we won't spend hardly any time talking about it. What is the product of that reaction? An ester. Good. You should be good enough at this point that outcome is obvious to you. You should be pretty good at recognizing that this is the tetrahedral intermediate, that a negatively charged oxygen is indeed a good enough nucleophile to attack directly. Once you get to that tetrahedral intermediate, what happens next should be obvious to you, because chloro is a better leaving group than OR minus, and therefore chloro leaves, and you indeed end up with the ester product. And this is a reflection of what I said when we ranked the carboxylic acid derivatives in sort of order of reactivity way back in the beginning of chapter 13, at the beginning of class, and I told you it was easy to make a less reactive carboxylic acid derivative from a more reactive one. This is exactly what I was telling you, right? An acid chloride can react with an alkoxide or an OR minus nucleophile to give you an ester. All right. So we're not going to talk about all the various combinations of different reagents. For example, swap out a nucleophile and you can get a lot of different things from the acid chloride. What if I used an amine instead of an alkoxide? Could I get an amide? Yes, you should be able to draw that mechanism. It's not that hard. You should be able to follow through what happens based on your analysis of which is the best leaving group. What we do want to spend a lot of time talking about today are cases where it's not so simple. And so we'll start with actually the carboxylic acid. And we're going to start here because this one wasn't even really on our list. The carboxylic acid has a conjugate base which is called the carboxylate. We've talked about that before, and the carboxylate was sort of at the very bottom of our list of reactivity for carbonyl compounds, in part because it's not even an electrophile anymore. And if you think back to 351, sometimes you used carboxylates as nucleophiles in 351. Not electrophiles. That negatively charged oxygen that's on both, that negative charge that's simultaneously resonance delocalized on both oxygens, makes the carbonyl carbon really pretty electron rich. And so you don't use carboxylates as electrophiles. You can use the conjugate acid, the carboxylic acid, as an electrophile, but the essential problem here is that acidic proton. So supposing we wanted to make an ester out of a carboxylic acid, let's attempt the approach that we used above with the acid chloride, and you'll see at once why this is a terrible idea. You want, presumably, to make the ester, you would need attack on the carbonyl carbon, But here, carboxylic acids are plagued by the presence of that proton, which has a pKa of around 4. And when proton transfer can happen, it usually is very fast. Proton transfer. So instead of the alkoxide oxygen attacking the carbonyl carbon, it will instead attack the relatively acidic proton to do the simple acid-base reaction that you've been doing since chapter 2 of OChem. And guess what, friends? We just made the unreactive carboxylate. So we went downhill, just down the wrong hill. And so dealing with this acidic proton is going to be the main feature for reactions involving carboxylic acids. Nature has to do this too, and I'll show you how nature deals with this a little bit later in the chapter. But first, how do chemists deal with this? So if we wanted to make an ester, one strategy for using the carboxylic acid is to use acid catalysis. In other words, we're going to cheat because we're not going to have the alkoxide deprotonate the carboxylic acid because we're not even going to use an alkoxide. We're just going to use an alcohol. The reaction that we'll talk about, those of you that are taking 353, the organic lab, may recognize as the Fischer esterification. Come on, it was fun, right? Fun? Yeah. I loved that lab, actually. That lab's what made me want to be an organic chemist. There was some reaction, maybe you've done this too, those of you that are in 353, it was called the Williamson ether synthesis. Back in the day, we were making a molecule that smelled like black licorice. It was methylanisol or something like that. And I'm a klutz, and so I spilled my reaction product all over the lab bench. And I was feeling kind of bad about it, but then Mrs. Hinshaw, the lab teacher, came along, and you had to know her. She's fantastic. But she was also scary. And so I was kind of scared of her, but she said, your product is right there. It's just all over the bench. Soak it up with some paper towels and then extract them, which was totally new to me. I didn't know that you could wipe up your product with paper towels, stuff them in a beaker, pour all kinds of organic solvent, squeeze the paper towels out, and then blow off the organic solvent with a stream of nitrogen. And ta-da, my product was still there, which was really kind of exciting to me. Which is why my job is a good fit, right? So anyway, Fischer esterification, you're going to start with the carboxylic acid, and you're going to start with the alcohol, but we're going to use a catalytic acid. And again, your choices here, probably it needs to be organic soluble. You don't want to use an aqueous acid because water is a product of this reaction, and those of you that have done this in the lab know that you need to actually have a strategy for removing water. In the lab, what was it? You remember? Silica gel, which actually just, it's this sand-like stuff that sits in the bottom of your flask and soaks up the water. A lot of other strategies you can use, distillation's one of them. On the small sort of lab micro scale, that's actually a great solution, but that's why you don't want to use an aqueous acid. So even though the players are different, this is the same old story that you saw before in chapter 15 when we were making acetals. In the presence of an acid, the first thing to happen is you protonate the carboxylic acid, thereby activating the carbonyl carbon as the oxonium ion. You see the cheat here? We don't want to go to the carboxylate, which is really unreactive. We can't use a strong nucleophile because that's just going to deprotonate the carboxylic acid. So instead we cheat. We're using acid to protonate the carbonyl, turning it into this much more reactive oxonium ion, which now is electrophilic enough for a neutral alcohol to attack. That first acid-base step is an equilibrium. This second step of ester attacks to give us a tetrahedral intermediate is also an equilibrium step. As you recall with acetal formation and acetal hydrolysis, what happens next once you get to this tetrahedral intermediate is dependent on where the proton is and what the good leaving group is. Of course, either of these electrons on the lone pair electrons on the oxygen could kick down and kick off that alcohol as a leaving group, but that would just be the reverse step. Instead, if we use the conjugate base of our acid, we can deprotonate the oxonium ion that has the proton on the OR group. That will take us to this neutral intermediate. We won't call it a hemiacetal because it's not. It's got 3 oxygens on it instead of 2, but analogously, if you're thinking back to that acetal formation mechanism, it's pretty close. Ultimately, we want to get rid of one of these OH groups, so we're going to use the acid catalyst to protonate the OH group, one of the 2, doesn't matter, they're identical, thereby turning it into a good leaving group. Okay. At that stage, either of these 2 oxygens can act as the kicker-offer. Doesn't matter which. You can draw the structures that lead from each of them, and they are actually resonant structures of each other. So I'll just pick one. We kick off water as a good leaving group, and that leads us to this oxonium ion that looks a lot like the one we started with, only we've replaced the OH with an OR using this addition, proton transfer, elimination type chemistry. And then lastly, we will restore our acid catalyst by using the conjugate base of our acid to deprotonate the carbonyl oxygen, and that, that gets us there. I should point out that this is the stage at which water leaves, and that's where you need to remove water. That will drive the equilibrium forward to forming the ester. Okay? Just like acetal formation, this reaction is 2 reactions in one because you can start with the ester and under strongly acidic aqueous conditions, you can hydrolyze the ester to go back to the carboxylic acid and the alcohol. So acid catalyzed ester hydrolysis is just the reverse of Fischer esterification. As with acetal formation versus hydrolysis, the key feature is, are you removing water or are you supplying an excess of water? That may be one of the longer mechanisms you've seen so far. Don't worry, it will get worse, but for now, that's a pretty good one. What questions do you have about that mechanism? Go ahead.
Before you got to the oxonium and the lone pair electrons on the oxygen transferred to the pi bond and then kicked off, did it just kick off one of the protons? My question is, because we had 2 protons before the oxonium ion, and then in the oxonium we just have to restore the acid catalyst.
Here.
The last 2.
So this proton here is the one from the OH group.
Yeah, we have the H2O plus.
Right.
And then.
Which leaves as neutral water.
Okay, I see.
Yeah. Right.
So that alcohol is the one that became the. Okay, gotcha.
Yep.
Thanks.
So this one becomes this one. Yep. Good. Yeah.
Can like a second alcohol attack oxonium?
Great question. Can a second alcohol attack this oxonium ion, the second oxonium ion? Well, yeah, here, so that we generate an intermediate that looks like this. And the answer is yes. That can happen. And you don't want to know this. Your text doesn't describe it, and I'm not going to teach you how to do it. But such things are known, and just as with an acetal, you can get 2 OR groups on the carbonyl carbon. You can also get 3 OR groups on a carboxylic acid. That is called, since you asked, an orthoester. That'll teach you to ask questions in my class. That is called an orthoester, and they have various uses as basically ways to get to oxonium ions that are reactive intermediates. Don't worry about that. You can go ahead and forget that, but it does exist. Okay, yes?
Did you see the electrons on the OR instead of on the IR?
Yes, yeah, if you wanted to have, I'm not going to redraw the arrows, but if you wanted to have electrons from the OR group do the kicking off, that would lead to this resonance, that would lead to this, which actually is just a resonance structure of the oxonium ion. And you get to that by doing that. So either one leads to the same thing. Saw another hand back there? Same question, all right, good. What else? Yes?
So the oxonium has 1 OH, whereas the acetal has 2. Is that correct? I'm trying to remember the classification.
Well, so an oxonium ion is a word for any positively charged protonated oxygen. So technically, this is an oxonium ion, so's this, and so's that. Acetals aren't on this slide here because acetals are the products that we get from ketones and aldehydes, and we started with a carboxylic acid. What I said was that this intermediate, whoops, I'm erasing, that's not good. That intermediate resembles the hemiacetal. I will draw that just briefly for you here. A hemiacetal has an OH and an OR on it, and then these two things are the two things that were on the carbonyl, the aldehyde, or the ketone to begin with. Yeah. So just by analogy, we don't call this intermediate a hemiacetal, but that's sort of what it looks like. Okay, others? So that's ester formation, Fischer esterification, and acid catalyzed ester hydrolysis. I showed you why we can't make esters under basic conditions, but we can hydrolyze them under basic conditions. And since we just talked about formation of esters, I want to take a minute just to step away from carboxylic acids, and then let's use esters as our starting material. And I'll show you a second way to hydrolyze esters. So maybe I'll drag this down. If you want to hydrolyze an ester, by that I mean convert an ester back into a carboxylic acid, you sort of have 2 options. The first is acid catalyzed ester hydrolysis, which is just the reverse of Fischer esterification. I'm not going to draw that mechanism for you. You should be able to do that based on the mechanism I drew for you up here. The second option is called saponification. And why is it called that? Well, that root word comes from the same word that we use for soap. And ester hydrolysis, basically under basic conditions, that was an unintentional pun. I am amused at myself. Under basic conditions leads to hydrolysis of the esters. So let me show you how this works. This is a pretty simple reaction, but it's turned out to be pretty useful. We will use OH minus as our nucleophile. And so this is going to proceed basically how you would expect. OH minus attacks the carbonyl carbon. Lone pairs on the negatively charged oxygen attack the pi star on the carbonyl carbon to give you a tetrahedral intermediate. We're okay with that because a negatively charged oxygen nucleophile ought to be able to generate a negatively charged tetrahedral intermediate. At that stage, you have 2 options for leaving groups that can leave. If we kick off the OH group, that's going to simply take us back to the starting material. And that happens, that's why I've used the equilibrium arrow. However, if we instead kick off the OR group, that will take us forward to this product, but I'm actually not going to call it a product. I'm going to call it an intermediate for reasons that should become clear in a moment. Why do you think I have not used a reverse arrow for that step? What do you think happens as soon as that OR minus group comes off? Does the simple acid-base proton transfer, like I told you, was a problem for carboxylic acids to begin with. And that actually removes the proton, and you make as the product not the carboxylic acid, but the carboxylate, followed by the alcohol. Now, there are strategies in chemistry if you want to get the if you want to get the acid form of this carboxylate. It's a simple matter of adjusting the pH. We just learned that last time, right? If you adjust the pH higher than the pKa of that carboxylic acid, that proton's coming back on. So if you wanted to get the carboxylic acid at this point, you could. Yeah?
Do we need to know for conformation, do we need to know when the arrows are in equilibrium?
Yeah, the question is, do I need to know whether to use equilibrium arrows or not? I do that for your edification. I don't think I've ever asked a question on a test about whether or not this arrow should be in equilibrium. I certainly could ask whether you might think a reaction is reasonable if it's reversible or not, but right. So the product here is a carboxylate. Now, what has this got to do with soap anyway? But before we answer that question, any questions about the mechanism? Okay, students of history, how do, or perhaps YouTube tutorials / people that have their own Etsy stores selling soap, how do you make soap? Anybody know? You use lye. What is lye? Lye. Lye is actually just, it's often potassium hydroxide, but it's NaOH would work too, okay? So then what else do you use besides lye? I'm hearing animal fat. Okay, you can use a lot of things, any lipid, any triglyceride. Let me show you what animal fat is. Animal fat is a 3-carbon alcohol called glycerol. And each of the oxygens of glycerol is tied up in a long chain hydrocarbon. Usually in fats and oils from nature, these have even numbers of carbons. That is a feature of the process. It comes from how they're synthesized, and we are going to learn that this semester. But for now, let's see, 2, 4, 6, 8. Oh no, 2, 4, 6, 8, 10, 12, 14, 16. Okay. We got to do it again. 2, 4, 6, 8, 10, 12, 14, 16. Are you tired yet? That has something like 16. That's close enough. All right. So this is called a triglyceride. I feel like the room is literally trembling at the awesomeness of what we are learning here. There's some pressure building up in the sink that's causing it to shake. Glyceride. A triglyceride, just so you can stay oriented relative to what we've got before, above, I'm going to highlight in purple the alcohol portion, and then I'll highlight in orange the carboxylic acid portion, okay? So what happens when, and people on the frontier used to get big kettles and dump lye in them and put animal fat in them and then start stirring and under heat. And if you do that, what ends up happening is the same reaction we just described above. You liberate the 3-carbon alcohol, that's glycerol. Sometimes that has various purposes. And then what you make are 3 of these long chain hydrocarbon carboxylic acids. So, I'm not gonna have enough room, am I? So you need 3 of these carboxylic acids that have 2, 4, 6, 8, 10, 12, 14, 16 carbons. All right, and that turns out that carboxylate has what are called surfactant properties. You can use it as a soap. And the reason you can use it as a soap is from something that you learned in 351. This is a molecule that has a nonpolar tail that's quite long, and then it has a polar head group. What did you learn in 351 about nonpolar groups and water? You learned oil and water don't mix, right? Remember why that is? It was complicated. Some of you were saying intermolecular forces, good. It's related to, true or false, it's related to the super strong van der Waals forces between the nonpolar tails. False. Van der Waals forces are weak. So what drives oil and water to not mix? Entropy. Somebody said entropy. Good. That's always the answer? Maybe. That's right. Jesus is always the answer. That is true. He reverses the forces of entropy in our lives. That's good. Are we working on a lesson or something over there? Good. So the way it works, as you may have learned, is that when nonpolar groups are exposed to water, they take up space that water molecules can't take up, and the water molecules in the immediate surroundings have to accommodate it. They can't interact well with the nonpolar stuff, so they grab onto each other a little more tightly, and it forms a tight water sort of cage, an ice-like cage of water molecules surrounding the nonpolar portion of another molecule. That lowers the entropy of water, and so it's actually favorable for all the nonpolar portions of a molecule to get together to exclude as much water as possible. You learned about that in 351, and probably if you take 481 biochemistry, you'll learn about it again. The polar head group, however, by virtue of its polar oxygens and the fact that it's negatively charged, can hydrogen bond with water, and so you end up with what is called a micelle. We could abbreviate this nonpolar, with this soap molecule like this. It kind of has this conical shape. It's wider at the top and then tapers towards the end. And this allows individual carboxylic acid molecules to associate into sphere-like particles that are called micelles that have a polar exterior and a nonpolar interior. And these micelles can dissolve and carry away grease, oil, other nonpolar molecules, just because they're nonpolar on the inside, polar on the outside. They're perfectly soluble in water. So our ancestors have been using this as soap for tons and tons of time, but it's based on a reaction that we know, saponification. Okay, any other questions? Any more you want to say about that? Yeah.
So is the grease molecule in the middle?
Yeah, so the greasy stuff would tend to be the nonpolar tails of each of these carboxylate groups are in the middle, and other grease molecules could be imported into the interior and then float away.
Is it like trapped?
Yep, trapped. Okay, what else? Good. So that's saponification. There's more that we could talk about there, but I think maybe I'll hold off on that for a little bit. Let's now talk about the amino version of an ester, which is called an amide. I'll draw an amide for you. This is an amide. It's a derivative of a carboxylic acid because it has the same basic structure, only instead of an OH here or an ester, we have this NRH group. And actually, in an amide, these could both be hydrogens, they could both be carbons, or one could be hydrogen and the other could be carbon. It just depends on what amine we use to make the amide. Amides are really low on our list of reactive carboxylic acid derivatives. They are pretty stable and not so reactive. And so there are only a few things that we do with that we can do with amides, and I'll say more about that a little bit later. I want to focus our discussion again today on if you wanted to turn a carboxylic acid into an amide, how would you do it? And the answer is kind of a problem, because as we did with the esters, the basic problem of a carboxylic acid is that acidic proton. So again, if you just brought an amine, this is a primary amine, so just a R group attached to NH2, into the presence of a carboxylic acid, the very first thing that happens is acid-base chemistry, and that's full of proton transfer. That's fully predicted by the difference in pKa's between these groups. So the amino group deprotonates the carboxylic acid. The carboxylic acid becomes the carboxylate. The amine becomes the ammonium. Ammonium is the word we use for a nitrogen like this that's attached to 4 different things and got a positively charged nitrogen. We call this the ammonium salt of the carboxylic acid, and you're sort of stuck there. Your text says there's something you can do with that. If you turn up the temperature, you can get a reaction to happen, though in practice that's not what chemists do in the lab, and that's certainly not what biology does. So I'll show you what chemists do in the lab, and then we'll get to the subject of what biology does. As before, our strategy is going to be to sidestep the acidic proton on the carboxylic acid. Now, we don't do acid catalysis here, in part because the amine is a base. You'll recall when we were going to do this with the ester, when we did acid catalyzed ester formation, Fischer esterification, the first step involved protonation of the oxonium ion. It's problematic here if we use a lot of acid catalyst, because the amine itself is a base, and so the amine would remove the proton instead of having the proton be on the carbonyl oxygen. So our strategy 1 for amide formation is really a cheat. We're going to turn, both of our strategies are cheats. We're going to turn the carboxylic acid into something else that's a good leaving group, and then we'll make the amide bond. So the first strategy is using a reagent that you encountered in 351. You maybe hated it then, but there it is, and it's back. Sockle. You got that confused with a number of other things. There was sockle, there was pockle, there was toluene sulfonyl chloride. A lot of things to be confused about. You can memorize this reaction, and that will be fine. In fact, I won't show you the mechanism of the reaction. It may or may not be in your text in a lot of detail. I won't hold you responsible for that mechanism, though I'll show you a key step so you can sort of have an idea of what goes on. So this is an intermediate several steps along the way. Oops. And again, if you want to just memorize this reaction, that's fine. One of the reasons it works, though, is the reagent SOCl2 converts the OH group into a supercharged spring-loaded leaving group. And by that, I mean that at this stage, Cl-, which is not a really great nucleophile, can attack the carbonyl carbon to give you a tetrahedral intermediate. And that can happen because what I've highlighted in green is such a super good leaving group. The reason it's such a super good leaving group is as it is leaving, as the electrons from the negatively charged oxygen kick down and the leaving group leaves, turns out the leaving group itself falls apart. The oxygen that's leaving essentially becomes another kicker-offer to kick off chloro as a leaving group. And so the other things that are formed in this reaction, in addition to the acid chloride, are Cl minus and SO2, which is a gas and bubbles off, and that dramatically increases the entropy of the reaction, which provides a strong driving force for going forward. So Sokal is our sort of cheat reagent because it takes the carboxylic acid derivative, it sidesteps the acidic proton, and it turns the carboxylic acid derivative into an acid chloride. And then, once we're at the acid chloride, we can do whatever we want with that acid chloride, including making an amide bond. So that's one of the things I think I told you at the beginning of the lecture is that, yeah, we can take, because chloro is such a good leaving group, we can react the amide with the chloro via a tetrahedral intermediate to do a substitution reaction where this is the product, okay? I'm not going to show you that mechanism. You should be able to walk your way through it. There's probably a proton transfer in there that you need to take care of. Notice that the amine comes with 2 protons, but in the amide product, there's only 1. If you want to use, your text will often show HCl as the byproduct, and that's fine if you want to use chloro as the base. Sometimes your text will say that you use an excess of the amine, and that's because if you do that, then instead of Cl minus, which is a really cruddy base doing the proton transfer, you can just use the excess amine to remove the extra proton. Okay, so that's one way. It's sort of cheating. Convert the carboxylic acid into an acid chloride, and then you can do whatever you want to the acid chloride, including making amides. So if you wanted to make an ester, you could do it this way too. I'm just not going to write down all the possible things you could do with the acid chloride. Any questions about that? Okay, that's a useful reaction to know. Oh, yeah, go ahead.
Just to make the acid chloride, do you need to make it carboxylate?
Do you need to make the carboxylate first? Looking in my notes, and I'd have to check back at the text, I wouldn't be surprised if people included some amount of a non-nucleophilic base to help that process happen. Though something like pyridine, though let me just check and see if I can find it quickly. And I can't. So, oh, no, it looks like your text doesn't report that a base is needed. You're right, I would think probably we turn it to the carboxylate first. And probably if you were to go read in the literature and see, I'm not talking about the English literature, I'm talking about the chemical literature, see people using this reaction, probably they do include a base. I'll just put that in parentheses. You'd want a base that's not going to act as a nucleophile. If you care, pyridine is a good example of one that you can use for that purpose. It's not described in your text, so I'm not putting it there, but yeah. Okay, others? All right. Well, next we'll talk about, yeah.
That's a one-step reaction, right?
Yeah, one-step reaction. Although overall, if you want to the amide, it's 2 steps. You first go to the acid chloride, and then you bring in the amine to get to the amide. Okay. Second, for amide bond formation, is the strategy of using, and I'm going to call this a coupling reagent. The goal of the coupling reagent is, again, sidestep the acidic proton on the carboxylic acid, which I'm going to abbreviate like this. And second, you have to turn the OH into a good leaving group, which is a familiar theme. If you took 351, the whole theme of chapter 9, as horrific as that experience was turning the OH into a good leaving group. So we're going to introduce a new reagent here. As with a lot of reagents, it's going to have an acronym. and that you will probably sort of remember it by. And that reagent is called dicyclohexyl carbodiimide, or DCC for short. Now I know that's a problem because you already have a reagent that sounds like that, and that's PCC. PCC is pyridinium chlorochromate. That's from 351. That oxidizes alcohols to primary alcohols to aldehydes, and secondary alcohols to ketones. This reagent, though it sounds similar, doesn't do anything like that at all. DCC, dicyclohexyl carbodiimide, is a reagent that will accomplish these purposes for a carboxylic acid. So in a predict the products question, you will see, and again, I'd have to check your text whether it shows just DCC alone. Often you need a base, a non-nucleophilic base. A good example of that is triethylamine, which is we often abbreviate as N with an ET3. It's not a good nucleophile because if it attacks anything, it becomes positive. The nitrogen becomes positively charged. So this is a good example of a non-nucleophilic base. You basically need it to remove the acidic proton, but you use DCC, a non-nucleophilic base, and then you also use some primary amine, and that will generate the amide. Okay, you can just memorize that reaction if you want, though I remember taking OChem and being frustrated if a mechanism was known at not seeing it, because I always felt like if I saw the mechanism, I could basically understand what was going on. So I'll show you some of the mechanism. Let's check and see how much of it is in your text so that I sort of remind myself of what we're dealing with. There it is. The whole mechanism's in your text. Great. All right, I will follow along with what your text shows. Your text actually, as it did with SOCl2, it leaves out the presence of this non-nucleophilic base. That's fine. It makes that decision just to keep things simple. Just be okay if you see DCC as a reagent with triethylamine as another reagent as well, because in practice you often need both of those. All right, so I'll show you dicyclohexyl carbodiimide. It looks like this. Here's one of the cyclohexyls. This is the carbodiimide group. It's a carbon bonded to two nitrogens. It's like a diimine. I'm not sure why they call it a diimide instead of a diimine, but I didn't make up the rules, whatever they are. So you can expect this carbon to be something like a carbonyl carbon. You can expect that carbon to be electron poor because it's bonded to two nitrogens. And you can expect it to be even more electron poor after what your text shows happening, which is lone pairs on one of the nitrogens deprotonate the carboxylic acid. That turns the carboxylic acid into a nucleophile, a carboxylate, which is going to be a nucleophile in the next step. And that also has the effect of activating the carbodiimide, because now, and I'm going to abbreviate those if it's okay with you, those cyclohexyl groups as CY. You could just call them R groups and that would be fine too, but by the time I realized that, I'd already written CY and I didn't want to erase, and now we're wasting time talking about it. Now the carbonyl carbon is even more electron poor. And so what happens is nucleophile attacks electrophile. This is very much like an addition to a carbonyl step, only it's our carboxylate acting as the nucleophile. And the intermediate then looks like this. So here's that carbon. There's the nitrogen. And there's the other nitrogen. Okay? So we've taken care of the acidic proton, and though it is not immediately obvious to you, what's over here is oops, I didn't mean to do that, is beginning to be a spring-loaded, super stable leaving group. Remember, leaving groups are all conjugate bases of really strong acids. Good leaving groups are conjugate bases of really strong acids. And what you're going to see next is how this leaving group can leave as a neutral molecule. So to show you this, let's have now our nucleophilic amine, the molecule we want to attack the carbonyl carbon here. We'll do that. Okay, ooh, why did we change to blue? That was kind of fun. Attack the carbonyl carbon to get a tetrahedral intermediate. That's going to look like this. The neutral amine, after it attacks, is going to be positively charged. And then over here, you've got the rest of that good leaving group. Probably one thing that's going on here, though your text doesn't say it, but it looks like it's reasonable to me. You might have wondered, how is it okay for a neutral amine to attack a carbonyl carbon to give you a negatively charged intermediate? Look at what's really close to that negatively charged oxygen. You've got an NH bond, and there's the potential for some kind of hydrogen bonding interaction there that stabilizes the negatively charged oxygen. That strategy for making a carbonyl attack on a carbonyl compound more effective, enzymes use that all the time. They use hydrogen bonding groups to stabilize the negatively charged oxygen in a tetrahedral intermediate. Let's see. Your text abbreviates the following steps, but I'll try to show you what the evidence suggests is happening. It turns out that the lone pair electrons on the negatively charged oxygen kick down, and the leaving group leaves. At the same time as it leaves, that oxygen itself becomes kind of a kicker-offer. This carbon-nitrogen pi bond is broken, and this nitrogen picks up a proton off of that one on its way out. Ugh. The reason I'm telling you the evidence suggests that that's happening is if you count the number of atoms between the proton on the positively charged nitrogen and the nitrogen on the leaving group, it's 6. And 6-membered rings conform with very little ring strain, which means that two groups that are 6 atoms apart actually can get quite close to each other. So it's pretty reasonable to propose that nitrogen 6, as it's leaving, reaches back and pulls the proton off the positively charged nitrogen. Your text doesn't show that, mostly because they didn't want to figure out, I presume, how to draw such a lovely picture as I have just drawn for you. And you've got it here. The product afterwards, I'll show you, is the amide. And then I want to show you the leaving group that leaves. That's the oxygen, the 2 nitrogens. Both nitrogens are now bonded to hydrogens and cyclohexyl groups. And there's an oxygen-carbon pi bond. This is called dicyclohexyl urea. It is neutral and it is very stable. And this is why I called it an excellent leaving group. So that gives you your amide, takes care of the proton transfer, and delivers you your amide at the end of the day. Okay, that's where we'll end for today. I will see you Monday. Have a good weekend.